First, let's read about what they say about the Big Bang Theory. We're in Wikipedia under Big Bang. I'm going to read in the second paragraph about 4 lines down. In 1929, from analysis of a galactic redshift, Edwin Hubble concluded that the galaxies are drifting apart. The key word here is drifting apart. This is an important observation evidence consistent with the hypothesis of the expanding universe. Again, another key word, expanding universe. Okay, we're going to go down to singularity. And one of the reasons why they call it singularity is because everything that we know of in the universe was in one spot, compressed nice and tight. The part I want to read here is about how long ago it happened. The universe has an estimated age of 13.799 plus or minus 0.021 billion years. I put in a Word document the key words here. Key words are expanding universe. And also under Edwin Hubble, it says that the galaxies are drifting apart. The other key word here is singularity. Everything we know of is in this universe is in one location, compressed tightly. Okay, very, very dense. Okay, the other part I want to read here is how long ago it happened. Key word in the document was that it happened 13.799 plus or minus 0.021 billion years ago. Okay, this is a very, very tight spec. I'm very surprised that they would give a spec that tight. In order to get the maximum years ago, you take the 13.799 and you add the 0.021, which equals 13.810 billion years. To get the minimum, we take the 13.799 and we subtract the 0.021 and it equals 13.778 billion years. That means the Big Bang happened between 13.778 and 13.810 billion years ago. And in this presentation, we are going to use the maximum, the 13.81. We are now in www.bigbangtheory.com. Now remember that the universe, everything in the universe was in one spot, compressed, and about 13.81 billion years ago it started expanding. In this web page here, it talks about some misconceptions. There are many misconceptions surrounding the Big Bang Theory. For example, we tend to imagine a giant explosion. Experts, however, say that there was no explosion, there was and continues to be an expansion. Rather than imagining a balloon popping and releasing its contents, imagine a balloon expanding an infinitesimally small balloon expanding to the size of the current universe. And then we're going to move down to the Big Bang Theory, evidence of the theory. I'm going to read the second one here. Second, galaxies appear to be moving away from us at speeds proportional to their distance. This is called Hubble's law, named after Edwin Hubble, who was between 1889 and 1953, who discovered this phenomenon in 1929. This observation supports the expansion of the universe and suggests that the universe was once compacted, compressed in one spot. Now I'm going to talk about redshift. We're in Wikipedia under redshift. I'm going to read the first paragraph here and part of the second. In physics, redshift happens when light or other electromagnetic radiation from an object is increased in wavelength or shifted to the red end of the spectrum. In general, whether or not the radiation is within the visible spectrum, redder means an increase in wavelength equivalent to a lower frequency and a lower photon energy in accordance with respectively the wave and quantum theories of light. In the second paragraph, some redshifts are example of the Doppler effect, familiar in the change of apparent pitches of sirens and frequency of the sound waves emitted by a speedy vehicle. Okay, we click on Doppler effect. We go to another part of Wikipedia website, which is Doppler effect. You give some examples, and these, especially these first examples here, are for sound waves or any wave energy that goes through an object. If the object is going towards you, there's a compression in the wavelength, which means a higher frequency. If the object is going away from you, there'll be an increase in the wavelength and a lower frequency. Also gives here an example under a car horn. The first part here is when the vehicle is going towards you, blowing the horn, and the second part is second half of it is with the vehicle going away from you, and it has a lower frequency. Partway down that website, it gives an example of wavelengths effects in an object that is still in this first part here. Okay, now the wavelengths are equal because the object is not moving. Here the object is moving close to the motion of the waves. And the third one here, the object is going at the speed of the waves. And then the last one here is going faster than the speed of the waves. Okay, and in here, notice that the wavelengths are very compressed. Okay, and then in the back here, away from it, is very much expanded. And then of course, the fourth example here is even more expanded. But one thing I want to make real clear here: the Doppler effect with object going, sound or energy going through an object is different than the light waves. Okay, now the reason why I say it is different, I could give you an example here to show you that it's not the same thing. Okay, energy, the Doppler effect on a sound wave is not the same thing as a Doppler effect with light energy, light waves. Okay, to prove that, if you were in outer space, in the vacuum of space, and without electronic equipment, and you try to yell at somebody that's maybe just even a few feet away from you, that person would not hear you, because sound waves need to carry the energy, these molecules to bump into other molecules to bump into other molecules. Light is not so. Okay, light travels very well in the vacuum of space. Okay. So since they're acting different, you cannot say all the rules are going to be exactly the same thing. And later on, when I talk about the light and show you some example of how light is affected. There are other things that could cause redshift. A good example is if you look at the noon sun and compare it to the sun that's sitting in the horizon in the evening, the sun that's sitting in the horizon has a more of a reddish tint. That is because the red light could travel through the atmosphere better than the other lights, and therefore we get the red shift. It's not caused from traveling away from us, but it's caused from the atmosphere filtering out the other lights. A good example would be a comparison to a sound. A sound that we might be familiar with is that when somebody is having maybe a party a couple of houses down with all their doors and windows closed, they might hear a different sound than what we would hear. Similar, somebody that might be sitting in the car that's sitting beside us with the windows closed and they're listening to music, but we're hearing sound different than what they are hearing. One of the sounds that they probably would be hearing is this. The sound that we might be hearing is this. Now, if we go to the Redshift page in Wikipedia again, and we go down to about the middle of the fourth chapter here, scientists will admit this also. There exist other physical processes that can lead to a shift in the frequency of the electromagnetic radiation, including scattering and optical effects like atmosphere. There's also other things that are in the universe. Universe is not completely empty, even though it's a vacuum. There's dust particles, there's comets, asteroids, stars. There is even hydrogen. They emit to hydrogen being in most of the universe. Okay, and these things filter out the light, and it could give the impression of a redshift. Remember earlier when we were reading about the expanding universe near Big Bang? Also, Edwin Hubble, he made a comment that galaxies are drifting apart. Now, if we had two spaceships taken off from maybe a single location, but they're going off about 1 degree separation from each other, what are the chances of the two spaceships colliding? The chances are absolute zero because they are going away from each other. Under the Hubble side, under galaxies and interacting, we have a big old list of photographs, and some of these might be artist drawings, but I'm sure they haven't found all the colliding galaxies or interacting galaxies. But what they have shown here is quite a few. And what I don't understand is, if everything is going apart, how can this be happening? If you go on the Wikipedia website, under Andromeda, it mentions a little bit about Andromeda Galaxy and the Milky Way galaxies colliding, but that probably no stars or anything will collide. There might be a few, I don't know. And I don't think they know either. While the Andromeda Galaxy contains about 1 trillion stars, the Milky Way contains about 300 billion. The chance of even two stars colliding is negligible because of the huge distance between the stars. For example, the nearest star to the Sun is Proxima Centauri, about 4.2 light years away. Okay, but even NASA's website, it talks about the Andromeda Galaxy and the Milky Way galaxies, which is ours, is going to collide. NASA astronomers announced Thursday they can now predict with certainty the next major cosmic event to affect our galaxy, Sun, and solar system, the titanic collision of our Milky Way galaxy with a neighboring Andromeda galaxy. The Milky Way is destined to be a major makeover during the encounter, which is predicted to happen about 4 billion years from now. Okay, we won't be around, yes, but It's the fact that we're not separating. We're not expanding. Galaxies are colliding with each other. Okay? So to me, that's a problem. It seems like they're contradicting. They're saying one minute we're going towards each other, the next minute they're saying everything's separating. Okay? And that's a problem. We are in Wikipedia under list of the most distant astronomical objects. When we go down into this section here, notably distant objects, and we're going to take the data from this section here. To let you know what GOY means. GOY means 1 billion light years. Okay, and I'll explain the redshift, what the Z is, in just a little bit. I'm not going to go through all of these here, but I picked out 4 that I want to show you how I got the data. And also I want to read down in this section here, showing that this is not all the data or information that they have. As of 2012, there were about 50 possible objects Z80 or further, and another 100 Z equals 7 candidates, based on a photometric redshift estimate. Okay, so there is others. They don't show the whole thing here. And you want to click on the first one here. This is the most furthest object that they have seen up to this date of this article. If you click on a name here, it will take you to this website here and give you more information about that object. It also gives here the location of the object, which I will show you later, and redshift for distance and speed, and what type of object it is. So it's got a lot of information, some more than others. What I did was I made a spreadsheet. Okay, this rather than going back and forth on different websites, I put all the information here on this website, on this spreadsheet. The ones that I have in yellow is the ones that I calculated out based on the information that they gave. The 4 that we're going to look at here, so I can show you where I got the information, is number 1 TNC11, and then the SXDF ND 106-2, or 1006, and this one here, and this, or this one here, and this one here. Okay, now we go back. Here it gives, it says that the location is based on the J2000 here. If you click on that J2000, it'll tell you what it means. It's a Julian year of J2000. A Julian year is an interval with the length of mean year in the Julian calendar, 360.25. Okay. The date that they have in coordinate universal time of J2000 is January 1st, 2000 at 11th hour, 58 minutes and 55 seconds, .816. Okay, so that's the location on that day at that time, the Earth's position based off the UTC time. And at that date, at that coordinates that they give us back here, the right ascension and the declination is where it's located in the sky. Okay, we'll go back to this here. And if you want to know what Z is, you go to this website here about measuring distance, redshift relation, and it tells us here Z equals velocity divided by the speed of light. So if we have a velocity that's the same as the speed of light, Z will equal 1. So that means that the multiplication of the light speed that it's going. For example, we're going at a velocity at twice the light speed, and we divide it by the light speed to get the CO2, meaning it's going twice as fast as the light speed. If we go half the speed of the velocity of light, and we divide it by the speed of light, z will be 0.5, meaning it's going half the speed of light. Okay, I want to go over to these other ones that we're going to be using for this discussion. Is the SX-NB 1006-2. Okay. Some have more information than others. It does give the location here, and it does give the redshift, which is information that we want to use. Okay, back to this again. And we also want to use the data from PDF. Here, we click on that, and it also gives the information about the location and the redshift, which I wrote down on the spreadsheet. Go back here again. We're going we use the IOK-1, and it gives information on it also. But some of these back here are missing information, and so I couldn't put it down on the spreadsheet. We are now back to the spreadsheet. The area that I want to cover right now, I just want to do number one to explain what these categories are and how we came up with it. The clear here, information that they have given. The yellow here is information that I calculated by the information they have given. Since this is the farthest galaxy that we have seen so far, I want to use this row as the example. When we're looking at this galaxy, we're not seeing something that is happening today. This is something that in this galaxy that happened almost 13.4 billion light years ago. And to figure out what percentage of the way we're looking back into the Big Bang, means that 100 would be looking at the Big Bang, and 0 would be looking at what we have right here, right in front of us. What we do to come up with this information, we'll take E3, the distance that the galaxy that we're seeing, how far away it is, and how far after the Big Bang that we're seeing in years. Okay. What we're looking at when we're looking at this galaxy today is we're looking at something that was 420 million years after the Big Bang. So we take this category here and we divide it by this category here, and we come up with and we times it by 100, and we come up with a percentage of the way that we're looking back. Further, 3% further would make it so that we could see actually the Big Bang. Years after the Big Bang. How we came up with that is that they said the Big Bang was 13.81 billion years ago. And so we'll take and subtract what we're looking at this date. We're looking back at 13.39 billion years ago. So we take that, subtract it from the 13.81, and that tells you what year we're looking at. Let's say the Big Bang was year 0. Okay, and this here would be year 420 million years. The speed of the Big Bang, how fast it expanded. Okay, since we're looking back in time, and what we're looking at is 420 million years ago, and the galaxy's distance is 13.39 at this date. Okay, so we're looking back in time to something that's 420 million years after the Big Bang. you got to remember at year 0, everything in the universe was in one spot and compressed nice, real tight. Okay? And all of a sudden, at 13.81 billion years ago, it expanded. At 420 million years after the Big Bang, it reached a distance of 13.39 billion light years. That's a really, really fast expansion. And with that being in mind, the object would, on the average, would have to go at 31.9 light speeds. 31.9 times faster than light on average. Now the Z that they have here saying that at the time that they looked at it, it is going 11 times the speed of light. That would mean that part of this, on the average, especially in the beginning part probably, would have to go faster than this. And to get the average for the light to from the beginning and with the speed down to the average and come down to 11.09 and still come out with an average of 31.9, it would have to almost go at the beginning 52 times faster than the speed of light. Okay, this sounds like sci-fi. Okay, this is like Star Trek stuff. Okay, and every place that I looked in on a website that talks about light speed, that nothing can go faster than the speed of light. But yet we're going, what, 50, and especially in the beginning, 50 times faster than the speed of light. And if if you notice here, the further away we get, the faster the object on the average was going. Okay. Now, if for some reason they're able to see to 13.8 light years, numbers would become unreal. This right ascension and declination, I put here with the two greens here, and compare the two with the angle that we're looking at. Okay, and 2 orange, I also did the same thing. And I put the number on the top of each color here. So between the 2 greens here, we're looking at 148 degrees right ascension between these 2 here, the 2 green. And a declination, we're seeing between these 2, we're looking at 153 degrees. And I'll show you that in the animation in just a minute. Okay, with the 2 orange here on the right ascension, we're looking at 166 degrees, and between these 2 here, we're looking at 158 degrees on the declination. Okay, and you say, well, what's that mean? Okay, that means that this is really close to 180 degrees. It's only 14 degrees off from being 180 degrees. That means they're looking in one direction here at something that's going away from us at 13 times or 7 times the speed of light, according to what they're saying, and almost 7 here at the speed of light. That's going away from us, almost 180 degrees apart, which kind of gives you the impression that they're saying that we must be in the center of the universe. Okay, I know we're not in the center of our solar system. We're not in the center of our galaxy, but the impression that they give here means that these are almost 180 degrees out, that we're in the center of the universe, though. Okay, we can't really shift one way or the other, because then we'll be looking back at the Big Bang. Okay, I made a 3D diagram here of the directions of 7 of the galaxies that are 13 billion light years and greater away from our planet Earth. And you can see here that 5 is mostly going in one direction, and 2 is going the opposite direction, almost 180 degrees in different directions. It's real close. I got it on the Excel sheet, more detail on it. And since we're so close to the Big Bang, which is 13.8, there's really no room for shift one way or the other here. And it kind of gives you an impression if you're going 13 billion plus light years away this way and 13 billion light years or greater in this direction, which is real close to 180 degrees out, that we are the center of the universe. Now I know we're not the center of the galaxy, we're not the center of the solar system, but this really does give you an impression that we are the center of the universe. We are the center of the Big Bang. I have 2 photographs here of the 3D animation program that I showed you just a little bit earlier. And this shows probably just a little bit better because I have the colors here. The orange, the 2 oranges that you have here are the ones that show on the spreadsheet right here. And then we have the 2 greens that are these 2 here. And then, of course, the 3 blues that are these 3 blues here. So the colors here on the spreadsheet match the color on the photograph. Okay. Now we could see this is the side view and this is the top view. That is really close to being 180 degrees out. Same with the top view, it's almost 180 degrees out. This is a green, almost 180 degrees out. Not completely 180 degrees out, but close enough that it's pretty well on the opposite end. And like I said earlier, there's the 13.8 years, and some of these are, all of these here are 13 billion light years away or further. So to get to the 13.8, it would be really close to this right here, the circle, the 13.8 billion years circle, the big blast. Okay, and we really wouldn't have no room to shift one side or the other. So like I said earlier, it kind of implies that we're the center of the universe, because we're seeing both directions. We're seeing greater than 13 billion years, billion light years. We are in Merriam-Webster dictionary, and we're looking under speed of light. And in the definition of speed of light, it says here, a fundamental physical constant, that is, the speed at which the electromagnetic radiation propagates in a vacuum, and that has a value fixed by international convention of 299,792,458 meters per second. This definition is actually missing a part. The part that is missing here is in reference to what? Is it in reference to a point in the universe, or is it in reference to from the source of the emission? First, I'll explain to you what I'm showing here. We have a little sphere here that's going to be traveling along through all these points here. At the first one, we're going to be showing at the speed of light. When it reaches each point here, a light will be emitted, and it will expand here at the point of emission. This is assuming that the universe has control over the light speed. As it reaches each point, it'll expand here, and when it reaches this point over here, we'll pause it and then we'll kind of analyze it. So here, at each point, the light beam is being sent out. And we can see what happens here. Okay, let's pause it here. Okay, there's several things that we need to look at. At point 0 right here, we have 1, 2, 3, 4, 5, 6, 7 lights that were emitted, which is 8 through 14. Okay, we just received number 8 or 7 here when it reached 14. The other thing I want to look at here is, let's say that this is the sun and we're going around it here as it's traveling. Let's say our sun, in reference to a point in the universe, is going at the speed of light away from that point. If the universe had control over it, you'll notice here that if we were orbiting here and at this point, we would not be receiving any light. It would be totally black. The sun would be black to us. Okay. On this opposite end here, the wavelength has expanded. Okay. On the sides here, the wavelength has compressed. Okay. So it'll be more shift to the blue. This is a shift to the red. This is black. Okay. So we couldn't be going at the speed of light if this was a true model and be able to see this, the sun on this side and a wavelength change here. The other thing that I got the feeling that most people think that this is what's happening, but it can't work. Okay, if you notice here, when we were looking at the Doppler effect, let's say the duck swimming in the water, and the duck was going at the speed of the waves. This is exactly what it would look like. It's exactly the same thing. Okay, but you got to remember, light is not the same as wavelengths in the air and in water. In the air and the water, molecules bump into another molecule, which bump into another molecule, which bump into another molecule, and that causes the wave effect. We are now on the CubeCosmos website on about how fast does a space station travel. The International Space Station travels in orbit around Earth at a speed of roughly 17,115 miles per hour. That's about 5 miles per second. This means that the space station orbits Earth and sees the sunrise once every 92 minutes. Now this is people, ladies, that are in the space station, and even though the space station is going at great speed, in relation to one another, it seems like they're not moving very much at all. Now let's say that they had an instrument that could shoot out a projectile at roughly about 150 miles per hour in the direction that they are traveling in relationship to the Earth. If they shot it out to them, the object would be going about 150 miles per hour. But to Earth, you would add the 150 and it'll be 17,300 miles per hour. On the other direction, if they shot a projectile in the opposite direction that they're traveling at 150 miles per hour, it will still look to them the same as it's traveling at 150 miles per hour. But to Earth, it would look like it's traveling 17,300 miles per hour even. Okay, we're back to the animation. This time the light speed is in reference to the source, and the source is in motion. Just like the space station, when they shoot out a projectile, the speed of the object is in reference to the space station, but the Earth is seeing it different. Okay, now we'll start this animation. Right before the object is going to be moving at light speed up to about 7 here. Okay, and when the light expands, it'll expand in reference to the motion of the source. Okay, and let's see how this affects it. Okay, we'll pause it there. Other thing you'll notice here means that this object is going at light speed. No matter how far it goes, we're going to only see the very beginning motion here. Okay. Of course, the light will expand past it here. Now, this would make this direction here, that the light in reference to a point in the universe is not moving at all. Okay. And in this direction, since we're moving at light speed, this expansion here went twice the distance, so it means it's going twice the speed of light in reference to a point in the universe. Okay, and I believe this is what the light model is actually following here. Okay, now we'll go to the other one where it's going half the speed. Okay, now in this model here, the object will be moving half the speed of light. Okay, and the light will be still expanding, but in reference to the source here, which is in motion. Okay, now let's see what happens with this model with half the speed. Pause. 1, 2, 3, 4. Oh, sorry. Yeah, first light. 1, 2, 3, and roughly about a half. So even though it's in the position of 7 here, we only had received light from 3.5. We're seeing the light from where it was emitted right here. So if this went to 14, we only would be seeing the number 7 light by the time it reached 14. So we're seeing about half of what it actually had traveled. Back to the definition of the speed of light we read before. A fundamental physical constant, that is the speed at which electromagnetic radiation propagates in a vacuum, and that has a value fixed by International Convention of 299,792,458 meters per second. And I mentioned that this is not totally correct because it should give a reference to what. And so I added this, which is in yellow here, because it needs a reference point. Whether is it a reference to a point in the universe, or is it a reference to the source of emission? I gave in the animation samples of both, and I do believe that it is in reference to the emission point. So if that emission point is in motion, then the light speed is, as far as a point in the universe, could actually be going faster than the speed of light, or even go slower than the speed of light. So I rewritten this and I added in reference to emission point or object of the light source. In my research and checking about the speed of light, all the measurements that they took to find out what the speed of light is all in reference to the source of emission. If this being true, then if the source is in motion, then the light is being emitted follows that source. So that means that if the object is going the speed of light or faster, then light will never reach us. Okay? So any stars that are out there that we can see cannot possibly be going away from us faster than the speed of light. Okay, I made a little extension on our Excel sheet. What I did here was I put the galaxy that we see the furthest away at this current time, which is 13.4 billion light years from us. Okay, and that would put it at 420 million years after the Big Bang. But if in the future we even see further than that, for example, we saw a galaxy at 13.5, and I made the spreadsheet here, 13.6, 13.7, 13.8, 13, just 1 million years before the Big Bang, and at the Big Bang, just to show you what would have to be to make it get that kind of distance. Okay, they say that they're seeing this galaxy is going away from us at 11 times the light speed. So according to my calculations here, to get to that point in 13.4 billion light years, which is 400 million years after the Big Bang, it would have to travel almost 32 times the speed of light to get there at what we're looking at this point. Okay, and if we saw a galaxy at 13.5, that would put it at around 300 million years after the Big Bang. To get to that point, it would have to travel 43 times the speed of light, and so forth and so on. If we go down to 13.8, that would be 10 million years after the Big Bang. To get to that point, it would have to travel 1,380 times the speed of light. Okay, then I put, we're looking at a galaxy that's 13.809, which is only 1 million years after the Big Bang. To get to that point, it would have to travel 13,809 times the speed of light. Now, they haven't seen none of these yet, but if this in the future they do see this, I'm just showing you what would be. Okay, and if we see 13.81 billion years, billion light years away from us, we'll be looking at the Big Bang itself. Okay, and that would be impossible. Okay, if the reason why it wouldn't even be possible, because that would mean that it had to get that distance in the instant, not even a fraction of a second or a microsecond. It had to be instant. Okay, and that of course is mathematically impossible, and that's also impossible in physics. Okay, it takes time for something to move from one point to another. Okay, and in math, you would be dividing a number by 0. And that's undefined. You can't do that in math. Okay, and in physics, you can't be from one spot to another spot instantly. It's impossible. Okay, so I realize that they haven't seen these yet, but if in the future they do see it, you're going to realize that they got to start admitting that there's a problem with their theory. Okay. As far as I'm concerned, it's already just seeing this at 13.4 billion light years, this galaxy here, which we have seen and they had measured. To me, that's pretty well destroyed the Big Bang Theory.